Hello dear students, as you all know we are doing chapter number 5, Magnetism and Matter. In the last video lecture we studied how a solenoid is an equivalent to a bar magnet. Today we are going to study our next segment of the chapter. You can say the chapter can be divided now into two segments. Earlier it was 3 but this year some parts are deleted. So now the chapter can be divided into two segments. First segment we have done. Now we are moving to the second segment, and the second segment is Earth's magnetism. Earth's magnetism. Actually, there are some evidences, there are some practical evidences by which we can say that the Earth is having a magnetic field. And the study of Earth's magnetic field is called Earth's magnetism or geomagnetism. Geomagnetism. One more name is there, terrestrial magnetism. Terrestrial magnetism. Okay, all these are only the same, Earth's magnetism. The study of magnetic field of Earth, its reason, its cause, its pattern, how the magnetic field is, how magnetic field lines are there, is called Earth's magnetism or geomagnetism or terrestrial magnetism. What are the practical evidences by which we can say that Earth is having magnetic property and Earth behaves like a magnet? Let us see. The first evidence is, if a bar magnet is left free to rotate in a horizontal plane, then they stay in north-south direction. Okay, this is the property of magnet. You must have studied in class 10th, and we have discussed it in our previous lecture of this chapter also, that if a magnet is left free, suppose from a thread it is tied and now it is left free to rotate in a horizontal plane, then it always stays in which direction? North and south. Okay, suppose this is north, this is south. The magnetic bar always rests like this. It will not be like this, it will not be like this. It will stays in this direction only. Why it stays? From this experiment, what we conclude that there must be an external magnetic field due to which it experiences a magnetic force, and because of that force it stays in this direction only. There must be a south pole this side, so that its north pole is attracted toward this side, and there must be a north pole this side, therefore its south pole is attracted toward this side. And that's why there must be an external magnetic field line which is along this line, and this magnetic bar align itself with the external magnetic field. Right? From this point, we conclude that there must be a magnetic field line which is directed from south to north, so that south to north. Let me make the directional chart also. East, west, north, south. There must be a magnetic field line from south to north, due to which if a bar magnet is left to free to rotate horizontally, it stays in the direction of north-south. Okay, the end which rests towards north is north pole, the end which rests towards south is south pole. Right? The second evidence is, if a magnetic material, if a metal which can be a magnet, which can acquire magnetism, okay, if a metal is buried in earth for a longer time, period of time, then it behaves as a magnetism, a magnet, or it acquires magnetism. But this period is very long, okay, of 1000 year, 10,000 year, depending upon the material. So how that material acquires magnetism? It acquires because it has been kept in a magnetic field for a very long period of time, and because of that magnetism is induced in the material, and now the material behaves as a magnet. Okay? The third evidence is, if a bar magnet is kept horizontally in north-south direction, then neutral points are obtained nearby it. What is a neutral point? Neutral point is where the magnetic field is zero. Okay. Now suppose a bar magnet is kept like this. This is your north direction, this is your south direction, and bar magnet is kept like this only. What we observe, there are some points nearby the magnet where the net magnetic field is zero. These points are called neutral points, denoted by capital N. Okay. Now at these neutral points the magnetic field is zero, but it should not be, because it is a point where nearby a magnet. It simply means that there must be an external magnetic field which cancels the magnetic field of the bar magnet, and that is why the net magnetic field at this point is zero. So from all these 3 points we reach to a conclusion that there must be an external magnetic field which is present around the surface of the earth, and this magnetic field is the magnetic field of earth, which is called Earth's magnetism or geomagnetism that we have discussed, right? So these are the evidences which proves that there is the magnetic field of earth. Now the question is, why the magnetic field of earth is there? Why earth behaves as a magnet? So there are some theories. Earlier it was believed that, the first theory, it was believed that the earth consists of very large bar magnet at its center. Earth, suppose this is earth, okay, a bar magnet is there inside the earth. If it is geographical north, geographical south, here it is south pole and the north pole of the magnet. A very large bar magnet is present at the center of the earth, and because of this earth behaves as a magnet. This theory was failed because after some time it was discovered that the temperature inside the earth is very high, and at that high temperature no material can behave as a magnet. Okay, that's why this theory has been the material can be in the form of solid. That's why this theory is failed. Second theory which was there, it was believed that, now we have discovered that earth rotates about its axis. Earth rotates about its axis. With the rotation of earth, the atmosphere, the molecules present in the atmosphere, they also rotates. Earth rotates and atmosphere molecules are also rotating with the earth. We have a particular layer of earth that is called ionosphere, which consists large number of ions. When ion rotates, they make a current loop, and that current loop behaves as a magnetic dipole that we have done in the last video lecture. Okay, so this was the idea that with the rotation of earth, the ions also rotate, and if they rotate, they form an equivalent current loop, and because of that current loop, a magnetic dipole, earth behaves as a magnetic dipole. Now this theory was also declined, this theory was also failed because this ionospheres are at a very large distance from the center, and the rotational speed is not that much that it produces such a magnetic field of 0.1 Gauss to 0.5 Gauss. This is the value of Earth's magnetic field on the surface, right? So this current loop cannot produce a magnetic field of this strength. That's why this theory was failed. Next theory, it is believed that inside the Earth the temperature is very high, and now if the Earth rotates, then what happens? The material which are there inside the Earth, they also rotates. They also rotates with the rotation of Earth. Means core of the Earth is rotating, right? And in there, very large number of magnetic materials are present, and they rotates, ions are present. They rotates and they make a current loop, and now that current loop can produce this kind of magnetic field. But the problem is, this theory was failed, and this theory was accepted a bit. It is not the exact theory because the variation of magnetic field is so irregular, okay, that we cannot produce an exact theory why the magnetic field is there. But if you have been asked what is the reason, at class 12th level we can say that this is the theory which we have, that the ions inside the Earth, they rotates with the Earth, they behaves as a current loop, and because of that current loop we have a magnetic field. Okay, so this is how this can be the reason behind the Earth's magnetic field. Now let us understand some terms related to Earth's magnetism. The first term we are going to understand is geographic axis. Geographic axis. What is a geographic axis? Geographic axis, the straight line which joins the geographical North Pole and geographical South Pole. That straight line is called geographic axis. Okay, this is straight line which joins the geographical North Pole and geographical South Pole. This straight line is called geographic axis, right? The second thing we need to understand, magnetic axis. What is magnetic axis now? What is magnetic axis? So there is a straight line which connects the magnetic North Pole and South Pole. Now here we have to understand a bit. From the side in which geographical North is there, in that side magnetic South Pole is there, and the side at which geographical South is there, in that side we have magnetic North Pole. Okay, the distance between these two poles is about 2000 kilometers. 2000 kilometers. But as I have told you, this variation takes place. Okay, but this variation takes place in a very longer period of time. Now the straight line which joins magnetic South and magnetic North, okay, this straight line is called magnetic axis, right? This straight line is called magnetic axis. Okay, this is the center of Earth, and the angle between magnetic axis and geographic axis is 11.3 degree at the center. Okay, 11.3 degree at the center, right? So this is the magnetic axis, the straight line which joins magnetic north and magnetic south pole. This straight line is called magnetic axis. Third thing we need to understand, geographic meridian. What is a geographic meridian? The geographic meridian is a plane. The plane which consists, the plane which, and let me more correct, the vertical plane which consists geographical north and south direction, geographical north and south direction is called geographic meridian. The vertical plane, like suppose if I am standing over here, this is your east direction towards yourself, towards the camera. In this direction it is west, let this be north, let this be south. Basically this board is vertical and it consists the direction of north and the direction of south. Basically this board is your geographic meridian. A vertical plane which consists the direction of north and south is called geographic meridian. Next one we need to understand is magnetic meridian. What is a magnetic meridian? Again it is also a plane. It is also a plane and it is also a vertical plane. But what is this? What is this plane? Let us understand. Suppose if it is a bar magnet and it is suspended freely, then it stays in north-south direction. But now we know that North Pole and South Pole, they are not exactly in the geographical north-south direction. They are a bit tilted, you can say. So this bar magnet does not stay straight. This stays like this because north-south, this is a geographical meridian, but this magnet needs to move a bit because the magnetic north pole and the magnetic south pole is somewhere else, right? So this is not attracted towards geographical north, it will be attracted towards magnetic south pole, okay? And this end will not be attracted towards geographical south, it will be attracted towards magnetic north pole. So this will make an angle with the vertical geographical meridian, you can say. Now if a freely suspended magnet is there, then the vertical plane which passes through its axis, okay, is called magnetic meridian. In other words, let me clear first of all this. The vertical plane which passes through axis of a bar magnet, okay, axis of a bar magnet which is suspended freely is called magnetic meridian. In other words, you can say the vertical plane passing through north magnetic pole and south magnetic poles is called magnetic meridian, right? It is called magnetic meridian. Or in other words, you can say the vertical plane which passes through the axis of a freely suspended magnet is called magnetic meridian. Next thing we need to understand is equator, geographic equator, that you all know. Geographic equator, the great circle on the earth which divides the circle into two equal halves is called geographic equator. This is your geographic equator, right? And it is perpendicular to the magnetic axis. And the last one you need to understand is magnetic equator. Magnetic equator. What is that magnetic equator? Magnetic equator is also a circle which divides the earth into two equal halves, but the thing is it is perpendicular to the magnetic axis. It is a magnetic equator. right? So how the pattern of magnetic field lines are there? Magnetic field lines, how the magnetic field lines pattern is there? Just see, from the North Pole, magnetic field lines comes out, okay, and then they terminate to South Pole. So how the magnetic field lines are there? So from here the magnetic field lines come out and they terminate to South Pole. This is how the magnetic field lines are there of Earth. From North Pole they come out and from South Pole they terminate. Is it clear? This is the magnetic field lines of Earth. Okay? Now let us move to the last segment of the topic as well as the chapter. The last thing we need to understand is the component of Earth's magnetic field. The component of Earth's magnetic field. Let us understand. Next thing we need to understand is the component of Earth's magnetic field. Okay, or Earth's magnetism, you can say. The first thing we need to understand is, the first thing we are going to understand, magnetic declination. Magnetic declination. What is magnetic declination? As we all know that the geographical north-south direction need not to be coincided with the magnetic north-south direction. So there must be an angle between the magnetic meridian and the geographic meridian, because geographic meridian is the vertical plane which consists the direction of geographical south and geographical north, where magnetic meridian is the plane which consists the direction of magnetic north pole and magnetic south pole. Basically there is an angle between magnetic meridian and geographic meridian, and that very angle at a place is called magnetic declination. How we define that? We say that the angle between geographic meridian and magnetic meridian at a place is called magnetic declination. Magnetic declination. Second thing we need to understand is angle of dip. Angle of dip or magnetic inclination. Magnetic inclination. What is that? Magnetic inclination. Okay, just try to understand. If a bar magnet is free to rotate in a vertical plane, like suppose this is a bar magnet, this is free to rotate horizontally and as well as this can rotate vertically also. Then what we observe at a particular place, it does not stays in the horizontal direction. It stays a bit like this. It does not stay in the horizontal direction, it stays a bit like this. Basically, why it is going down? Because the direction of Earth's magnetic field is bending it from the horizontal. This is a bar magnet, this is a small magnetic needle, suppose. Why it is bending towards down? Because it get itself aligned along the direction of magnetic field of Earth. So basically what we can say, the direction of magnetic field at this particular place, if the magnetic needle stays like this, then the direction of magnetic field at this particular place is like this. This is horizontal, this is direction of Earth's magnetic field. So basically this angle, by the angle the needle gets dipped, that angle is called angle of dip. How we can define? We say that the angle made by Earth's magnetic field with the horizontal is called angle of dip, right? It's called angle of dip. Now let us understand all these with the help of a diagram. Suppose this is a vertical plane which denotes magnetic meridian. Right? And there is a vertical plane which denotes geographic meridian. This is a plane which denotes geographic meridian. Obviously, magnetic meridian and geographic meridian are not same. This plane denotes what? This plane denotes geographic meridian. Obviously, they are not same. The angle between geographic meridian and magnetic meridian is called magnetic declination. This is the angle we are talking about. This angle is denoted by alpha. So this alpha is called magnetic declination. What is angle of dip? Now this board, as per the diagram, this board is in the magnetic meridian, right? Whenever a magnetic needle is suspended freely, it will stays in the plane of board. Now it will make an angle with the horizontal also. Suppose this is the magnetic needle. Okay, this is the magnetic needle. This is north end, this is the south end. This magnetic needle does not stay in horizontal. It stays a bit bent towards the earth. And why it is bending? Because the direction of Earth's magnetic field is in this direction. This B is the Earth's magnetic field. What is the angle that Earth's magnetic field made with the horizon? This line is horizontal. So this angle denoted by delta, and this delta is called angle of dip. Okay. Now that component of B along horizontal, third component is horizontal component of Earth's magnetic field. Earth's magnetic field. Now we have a two component of B. One is along horizontal, one is along vertical. This component is going to be B cos delta, and this component is going to be B sin delta. The horizontal component of Earth's magnetic field is basically B cos delta, and it is denoted by BH. We have now BH is equal to B cos delta, which is our horizontal component of Earth's magnetic field, and BV, this denotes B vertical, it is denoted by B sin delta. You need to understand that B cos delta is directed from where to where. B cos delta is directed from where to where? It is directed from geographical south to geographical north. Remember this. Or in terms of magnetism, you can say from north of magnetic north pole to the magnetic south pole. Or from geographical south to geographical north. B sin delta, it is always vertical downward. Vertical downward. Always. B sin delta is always vertical downward. But this BH is always from geographical south to geographical north. Now if we square and add them, then B is equal to what? Under root BH square plus BV square. Or if we divide them, we are going to have tan delta is equal to BV upon BH. All these are formulas which are used in different cases. Right? All these 4 lines are formulas. So there are 3 components of Earth's magnetic field. One is magnetic declination, other is angle of dip, and horizontal component of Earth's magnetic field. Now variation of angle of dip we need to understand. The angle of dip. There are some important points you must know. Let us discuss those points one by one, and then after this chapter will be over. This chapter has become very small because of reduction of the syllabus. All the material part has been reduced, and that is why this chapter has become very easy and very small. So this is going to be the last lecture of this chapter. Today, maximum by tomorrow, the lectures notes will be updated in the description. Okay? Some points. First point, the angle of dip, that is your delta, angle of dip, delta is 0 degree, where at magnetic equator, 90 degree, where at magnetic poles. Why is it so? Just try to understand. Suppose this is your Earth, this is your magnetic equator. Okay, this is your magnetic south pole, and this is your magnetic north pole. How the magnetic field lines will be there? Magnetic field lines will be like this, from north pole to south pole. This is the magnetic field lines. Suppose if here a magnetic needle is kept, then the direction of magnetic field is like this. It will align itself. So it will here it will lie horizontal. For this surface of Earth, this is horizontal, and here, this since the magnetic pole is just downward, the magnetic needle will go like this. So here, with the horizontal, it makes 90 degree, and here with the horizontal, it aligns itself. That's why it is 0 degree. From here, one more thing we need to understand, that if someone goes from magnetic equator to magnetic pole, then angle of dip increases. If we go in the reverse, from magnetic pole to magnetic equator, the angle of dip decreases. Okay? One more thing, and the last thing. This magnetic equator, sometimes it is considered, we can take as geographic equator also, because the separation between magnetic equator and geographic equator is not that much large, and that's why sometimes it is being considered that the 0 degree is the angle of dip at the geographic equator, and it is 90 degree at the geographic poles. Okay, so after reduction of syllabus, only this much is there in your syllabus. Only 3 lectures I have taken to complete this chapter. This chapter has become very small. Okay, now we will start chapter number 6, that is your electromagnetic induction, a very interesting one, and how the current is being produced. Now we are going to study that in that chapter. Okay, so this is all for the day. There is no very difficult question in the NCERT. This chapter is very much theoretical, and that's why the numerical portion is not there very difficult. You can do your numericals by yourself. Only these formulas are there. Okay, you can do the numerical by yourself. So this is all for the day. This is all for this chapter. In the next video lecture, we will start the chapter number 6. Thank you.